Alright, ladies and gentlemen, so we are diving into 6.3 and looking into the concept known as integration by parts. Alright, so our goals for this section and all the videos that will accompany it are to derive, alright, the product rule in integral form, but more specifically and more importantly, to evaluate indefinite and definite integrals by parts, alright, by this thing called integration by parts. So my first question to you is, remember the product rule when we were doing derivatives. Alright, it was true that the derivative of a product of two separate terms was equal to the first term times the derivative of the second term, or dv dx, plus the second term being multiplied by the derivative of the first term. And of course you go in either order just because it is an addition problem in here. And so what we are going to be looking at in integration by parts is almost kind of the integral form of the product rule. And that's really what integration by parts is. Now, we're not going to spend the time to exactly go through the entire proof of how to go from the product rule of derivatives to the integration by parts formula, but a good kind of reference, if you do want to kind of check it on, is on page 341 of your book. You see exactly how we go from our step in blue, our product rule, down to our step down here in red and our integration by parts formula. Also, you can Google in Khan Academy, go to their YouTube page, and you can also find a great proof of how to go about integrating the product rule to end up with your integration by parts formula. But because we are, for our purposes, we are really focused on just the evaluation of integrals using our by parts formula, and that is what we see down here in red. So, right now you might be looking at this and not really quite grasping what all the integration by parts is going to be. U dv, it doesn't look too crazy and too different that we've done in the past. But notice the difference in the variable u and the differential dv. Alright? And so that is what really the by parts is going to end up showing us. We're going to kind of break it apart into a u and to a dv to almost get an integral version of the product rule. Alright? So what I want to do in this video is I want to do an example as to how and when do we use integration by parts. So let's start off the when. Well, usually when you see a product like you do here, we've gotten so used to finding that u, finding the u substitution as a way to integrate indefinite integrals. And it's great, and don't get me wrong, u substitution has to be used a lot of the times, but there are going to be some times where you're just struggling. You're trying to find that u that is going to actually make the integral evaluated, and that's all going to make sense when it's, in the end. And then there's going to be times where you're just struggling, and you're struggling. So where is that u? Well, more than likely what ends up happening is that you're not really looking for u. You're looking for an integration by parts formula, and that's what we have up here in red. And so this first example that we're going to look at is a very basic opener as to how to visualize a problem when you're kind of cued to use integration by parts. So before I go into how to describe what u and dv are going to be, I want to just simply solve this one, get your mind thinking a little bit, and then go back as to why did I choose u for blank and why did I choose dv for blank. Because like I said, our goal with integration by parts is we're going to separate to find a u and then to separate and to find a dv. That's the parts. They're the two parts, quote unquote, that we are looking for here. Alright, so let's dive right on. In example 1, the integral of x times the cosine of x dx. Alright, so as I'm looking through here, okay, I'm trying to find that u substitution. Do I want to make u x? Do I want to make u cosine? Well, none of them will end up giving me a solid du when it's all said and done. And so once I start to kind of realize, well, substitution is not going to work, how do I go about it? That's how we dive into integration by parts. All right. So it is true that we have the integral from or of u dv should be equal to u times v minus our integral of v with respect to u, or uv du. So where does v come from? All of a sudden we only have u. Well, where is there going to be a v coming on into place? Well, let me go ahead and identify a u and a dv first, and then let me think about where you can find v from. So let's take a look. What if I went ahead and in using my formula, I want to go ahead and acknowledge u as being x and dv as being cosine x dx, okay? And right now, you're probably thinking, why am I choosing that to be the u and that to be the dv, other than it looks like it goes according to the formula, right? And for some time, that is going to be kind of how it's laid out for us, but I don't want you thinking that's all the time. So by parts, my u part and my dv part. That's what I just broke it up into right here. Now, in order to fully complete the formula, all right, we take the differential of u, right, the differential of u du, and find the simplest antiderivative of cosine of x, okay? Because I have u, I have dv, but I don't have du. I need du in the formula, and I need v in the formula. Well, if I have u, I can pretty easily get to du, right? That just means the derivative. Well, the derivative of u would be du, and then the derivative of x is just 1, so it would be du is equal to dx, just like it was when we did our substitution. You want that du in there, okay? And now, if I have dv, I have the derivative of v. I don't want the derivative of v, though. I want v. That's what the formula tells us. I want the derivative, antiderivative of that. So I'm really going to be finding the integral, or the antiderivative of cosine of x. And so now, let's take a look here. This is going to lead me to show that v will be sine of x. That's the antiderivative. And if you're thinking, but wait, where is the constant of integration? Just hang on. The constant of integration is going to come at the end of our integration. Don't forget, the whole point of this was to find the integral of x times cosine of x dx. So, now, let's go through a little check. We've defined u. We've defined dv. We needed a du, so we went ahead and defined du. And then we needed a v, so we went ahead and defined a v as well. Okay, we're getting somewhere. Now, let's start utilizing the formula a little bit more. And so now, I don't want to cover it up completely. Alright, now let's take a look at our formula. So for our formula, the integral of u dv, well, the integral of u dv, that was our x cosine x dx, okay? And now we need to put in all the little parts. So I have u times v. U times v. Well, u is equal to x. V was sine of x. And then we have minus the integral of v, which is sine of x, times du. Well, du is dx. Hopefully you're starting to see why we have to start getting these different differentials. Because remember what we talked about, you cannot have sine of x du. You have to have the differential that goes in accordance to the independent variable. And so we can see why we have to start making these changes in here. And now, just kind of going through the remainder of this, to simplify it on out, there's nothing to do with x times sine of x. That is what it is. That's just part of the formula. And then you need to integrate sine. Well, the antiderivative of sine is negative cosine, but there already was a negative there, so that becomes positive cosine of x. And now our constant of integration comes into play. And so this is our final answer. All we did was use the formula for the integration by part. Okay? So, as I said in the beginning, I'm going to go through this example and then I'm going to kind of go through a little helper as to how to choose U and DV. And so this is using an acronym we know to be LIPET. Alright, LIPET. This is going to be our acronym as to how to choose a U. So if you've kind of been wondering, where did we choose the U from? This is usually, alright, a really strong usually. It's a great reference point, okay? It's a very great reference point. It's one of those things where I'm not going to sit there and say 139% of the time, but usually it is a phenomenal reference to get things started. The first choice to be U is the L, or a natural log, okay? If there's a natural log involved, that would be our first choice to make U, okay? Let's say there isn't one though, okay? Now let's go down to that next step. Let's say there isn't a natural log for us to use. And then we would look for some kind of inverse trig function. So option 2, would be inverse trig function, alright? So first choice would be the natural log. The second choice would be the inverse trig function. And then let's say if maybe that's not there, okay, we've tried the L, we've tried the I, things still just working on out. And then we go down to the possibility of finding the polynomial, okay? You look for a polynomial next. That's the third on the list. Alright, you've tried natural logs. You've tried your inverse trig functions. There's no polynomials. Next in your LIPET acronym, you are going to be looking for an E, exponential, okay? You're going to look for an exponential to use as your U. And so remember, as we're going through these, this is how to determine which one is going to be U. And so think about what we did in our last example. Let's finish off T, and then we'll go into our last example that we just did. And then our last thing that we are looking for is T, for trig function, okay? So let's kind of go through these. In our last example, we chose U to be X. Alright, well, why did we choose X over the cosine of X? Well, think about it, alright? In our LIPET acronym, the P for polynomial will come first as an option before T and trig function will come into play. So that's what we chose, X for polynomial. That comes first in our choices versus the trig function. Goal number 1, can you find a natural log? Goal number 2 would be to make U an inverse trig function. Goal number 3 was to make U a polynomial. Goal number 4 would be to make it an exponential. And finally, your last glory of hope, right? Last glimmer of hope would be to make U an a regular trig function, not an inverse trig function, a regular trig function there. All right. Alright guys, how about giving this one a shot on your own as we go into our next video. Let's go ahead and give this one a shot. So you're going to go and try the integral from x, or integral of x times sine of x dx, okay? Integration by parts. In the end, your answer should be negative x times the cosine of x plus sine x and then plus c. Check and see if this is your final result as well too, and we're on to the next one.